Okay, so shall we start?
I think we can start.
Okay, Vikram, shall I do the start?
Yeah, please go ahead, Raghu.
Yeah, so good evening to all of you. Today we have Dr. Nagesha from the Indira Gandhi Center for Atomic Research, who is going to talk as part of our InSIS webinar series of this year, 2023, on the topic of thermomechanical fatigue behavior of high temperature structural materials. To give a brief bio about Dr. Nagesha. Dr. Nagesha is scientific officer and the head of the Mechanical Metallurgy Division, which is part of the Metallurgy and Materials Group of Indira Gandhi Center for Atomic Research, Kalpakkam. He is also serving as an associate professor in the Homi Bhabha National Institute at IGCAR, Kalpakkam. He received his PhD in metallurgical engineering from IIT BHU, Varanasi. His research focus is on flow cycle fatigue, creep fatigue interaction, thermomechanical fatigue, and HCF-LCF interaction, mechanical ratcheting, structure property correlations. He has more than 80 plus journal articles and about 40 conference proceedings to his credit. He is a recipient of the DAE Science and Technology Excellence Award of 2017. He's also received the Best Paper Awards from the IIM Kalpakkam chapter in the years 2012 and 2020. He's got the DAE Group Achievement Awards in 2014 and 2015. He is a life member of the Indian Institute of Metals and Society for Failure Analysis, and I hope that he is also a member of the Indian Structural Integrity Society. So with these few words of introduction, I now request Dr. Nagesha to start his presentation. From what I understand, that his laptop camera is not in good shape. So we were trying to do some workaround, but it doesn't seem to be happening. So for those who have not met Dr. Nagesha in any meetings or something like that, you will have to bear with us on this, the fact that he's not able to show up his face on the screen. But otherwise, his presentation will speak a lot about his professional work over the last 3 decades, I think. So with this, I'll now request Dr. Nagesha to start his presentation. And those who want to ask any questions, you can type the questions in the chat box. We will take it up at the end of this lecture in a sequential order and then get it addressed by Dr. Nagesha. Thank you.
Yeah, thank you very much, Professor Raghu Prakash. And at the outset, my thanks to InSIS for inviting me to make a presentation of this monthly InSIS webinar. So I will basically talk about some of our works that we have carried out in the last few years, mainly pertaining to the thermomechanical fatigue behavior of different high temperature structural materials. So at the outset, I just want to give a brief background about the high temperature low cycle fatigue testing. So this gives shows the situation when we are in the process of starting up. This is a high temperature component. Typically, you can say it's a turbine blade. When in the starting time it's cold, so when the component is getting heated, surface gets expanded fast, but it is getting restrained by the interior, by the bulk. So this, what happens is we have a compressive stress being built into the component, because the pre-thermal expansion gets restrained by the colder bulk. The surface gets hot first, and then it is not able to, though it is able to expand externally, it is restrained by the colder bulk. So this gives rise to a compressive stress on the surface. And when the steady state is reached, the entire component gets heated up and it goes from compression, it drives it to tensile. So during the steady state operation, the creep, deformation, etc. taking place, and there is a relaxation of the stress. So this process this is the end of the cycle. So at the end, this is relaxation taking place due to the creep deformation, wherein we have conversion of some of the elastic strain into the plastic strain. So this leads to a reduction in the stress. So, and at the end of the cycle, at the beginning of the next cycle, the same thing gets repeated. So this builds up a hysteresis, stress strain hysteresis loop. I'm sorry for this. It gets shuffled frequently. I don't know. So this is what is the low cycle fatigue damage that is happening during the startup and shutdown cycle of this component. So next, low cycle fatigue. I don't know why it is continuously changing. Okay, the subject of low cycle fatigue can be broadly classified into two, depending on the temperature of testing. Generally, the conventional testing for generating the design-related data for high temperature structural materials that are exposed to fatigue in service rely on isothermal database that is generated at the constant temperature. Normally, if a structure goes from a T minimum temperature to a maximum temperature, normally the data for design relies on the results obtained from the peak or maximum temperature of cycling. This is an assumption, underlying assumption in this is that the peak maximum temperature cyclic data would give rise to a conservative life estimation. However, in the recent past, several studies have established that this need not necessarily be a conservative design approach. Hence, there has been a stress in recent years to generate data considering the temperature cycling that is actually happening in service. So, actual testing should be a thermal fatigue test rather than an isothermal cyclic testing. So here in the thermal, when you are having cyclic temperature situations, there are two kinds of tests one can have. One is the thermal stress fatigue, which is the actual scenario in the high temperature components, because the stress, as I have shown in the previous slide, the stress happens or stress builds up by the internal constraints. Constraining forces from the offered by the bulk of the material. So this is the thermal stress fatigue, which is actual situation that is happening in practice. But because there are a few complications with respect to carrying out thermal stress fatigue with incorporating internal constraints in the laboratory testing scenario. So considering this, a via media approach is taken, wherein we resort to thermomechanical fatigue loading, wherein the stresses are imposed by external force, by the pull rods. So but we have thermal cycling which is imposed, and the stress, instead of from internal constraints, the stress is applied through external. So this is an experimental simplification of the actual thermal fatigue, and here we have continuously varying unknown temperature and strain fields, which are actually not so simple in the thermal fatigue. So this is a definition. I just want to give a definition, as you everybody knows, but still, for the sake of completion, it is a gradual deterioration and eventual cracking of material by alternate heating and cooling, during which free thermal expansion contraction is partially or completely constrained. So as I said, internal or external. Internal constraint is what is happening in the actual thermal fatigue situation. This is also called thermal stress fatigue. And the external constraints is what is the case in the thermomechanical fatigue. So earliest studies related to thermal fatigue credited to mainly Glennie and Taylor, where Glennie has devised specific testing technique. It is actually this kind of when it's can say a turbine blade testing of a turbine blade for thermal fatigue. This is called this kind of thing is called as Glennie's discs. And there is a fluidized bed testing facility which was employed for this kind of tests, wherein this sample is changed, or shifted repeatedly from a high temperature region to a low temperature region, and this kind of test is a little bit complex testing setup, and there are drawbacks in measurement of stress and strain, both of them, which is not really that much simple, because it might require a lot of computational analysis, etc. Results obtained. Another important drawback is that results obtained from such tests cannot be expressed in a quantitative manner, and it cannot be really. One can get results related to a particular specific test specimen, or for specific situations only. It cannot be used for generating the generic database of thermal fatigue. So, in another important drawback is that in for thermal fatigue, actual thermal fatigue testing, you need to have a temperature gradient, wherein sufficient temperature gradient is required, for which you need a thick sample. So choice of specimen thickness becomes very critical. However, for the temperature variations in fast enough variation of this temperature, you need the thickness to be less also. So thickness in one from one viewpoint, thickness should be more, so that sufficient temperature gradient is established. But on the other hand, thickness should be less, because we can do tests at high enough cycling rates of cycling. So this becomes a problem. So experimental simplification of the more complex fatigue is through the TMF. So while carrying out the TMF, there are two extreme and basic temperature strain temperature waveforms deployed. One is called IP cycling, wherein with the temperature increase, we have the strain going from peak compressive strain to peak tensile, whereas the out of phase is the exactly opposite kind of situation. In practice, there could be a different phasing relationship between the strain and temperature in service. For example, this is the specific, like it can be a representative of the volume element of any high temperature component. In this case, maybe you can say it is a LMFP, liquid metal cooled fast reactor pressure vessel, wherein on the outside surface we see an in-phase
Hello?
It is not changing.
Is that a heavy slide?
Oh, okay. Okay. So it keeps changing. I do not know really why it is happening. Okay. So this shows different kinds of strain temperature sequence that is happening on the inside surface and the outside surface. Whereas inside in outer surface we have an in-phase relation. It can be it get balanced by the out-phase cycling on the inner surface. So we need to, since these are two extreme cases, these two cases will generally give rise to the extreme variation in the temperature. Hence, these two generally are used. Of course, there can be any number of combinations between the strain and temperature, but in general, these are the two things that are investigated. It is like in the creep-fitting interaction, tensile and compressive, peak compressive holds are normally investigated. Similarly, in thermomechanical fatigue, it is the in-phase and out-of-phase cyclic waveforms that are normally investigated. So, coming as you have seen in the previous slide, this is the in-phase TMF, wherein we have this red hysteresis loops. The mechanical strain is shown by the red, and this thermal strain is shown by green, and the total strain is shown. All three. Since it is all in phase, we can see that the total strain is the total of the mechanical and thermal. So in the case of OP, this is a typical hysteresis loop wherein you see that the thermal and temperature and mechanical strain are completely out of phase with each other, and the total strain is also given. A typical test setup that was used. I'll just give a brief outline about some of our tests that we have carried out on ferritic and austenitic stainless steel, including the weld joints also. This is the typical, this is the test setup that was used. We have used a 100 kN servohydraulic testing machine, which is equipped with RF induction and meter. And for controlling the temperature, we have for easy control of temperature, three segmented coil arrangement was used, using which the stress, the temperature was maintained within 2 to 3 degree dynamic temperature gradients along the length of the sample. And the type of sample used was normally for TMF one uses the thin sample or a hollow or tubular kind of sample with a wall thickness, with a very small wall thickness. In our case, we have used a wall thickness, 5 samples with a wall thickness about 1.4 mm, so that the radial temperature gradients are kept to a minimum, and a gauge length of 25 mm was selected, and in the gauge length, temperature dynamic temperature gradients were kept to a minimum within about 5 degree throughout the test. And when we are doing a completely reversed mechanical strain controlled TMF test, one needs to compensate for the temperature-induced strain. This is in practice done by different ways. There are but mostly time-based and temperature-based compensation procedures are used. Time-based employs pre-recorded thermal strain versus time, which is which is constantly accessed during the TMF course of the TMF cycling to obtain the real-time temperature or thermal strain component. But this kind of approach can possibly lead to control errors if some temperature variations are seen during even small variations in the temperature during cycle to cycle can give rise to problems or disturbance in this kind of approach. So in practice, normally what is used is the temperature-based strain compensation, which is generally more accurate and most generally used. And this is a temperature versus time waveform that we have got on our material. However, if too much of temperature variation is there between the along the gauge length, then we can get a lot of distortion. We will end up with a lot of distortion in the hysteresis loop, where from region to region there could be different local strain that is happening. Whereas see here, which center is typically here, it gives a situation where the problems situation wherein we have a hot region at the center, and there is another extreme of the gauge length which is much colder. And here a lot of difference in the plastic strain can be seen, and this kind of distortion in the temperature variation can give rise to a geometrical instability of the sample, which is different kinds of distortions can happen. This is typically one of the such problems can be seen in the form of instability of the specimen. There are barreling, and then there is local narrowed or regions which are highly deformed. So this kind of distortion also manifests in the hysteresis loops, wherein tips can be seen to be either blunted or heavily distorted. So what we have studied, we have given stress on the different aspects during the testing, the factors such as mean stress, dynamic strain aging, creep effects, and environmental effects, etc., have been investigated systematically. And I have told that IP and OP are the most basic and most normally investigated waveforms under TMF. Depending on how the life variation happens between IP and OP, there are different types of different cases. There are mainly some 3-4 types. Type I, wherein IP or in-phase loading gives rise to lower cyclic lifetimes compared to OP. So this is the predominant damage is the creep here, because maximum temperature coincides with the peak tensile strain. So when such creep or damage becomes more prominent, then type 1, this kind of situation happens where IP loading gives rise to a lower cyclic life compared to OP. Whereas situation when environmental effects predominate, the situation becomes reverse. So OP TMF tends to give rise to lower life compared to IP. And there are other two types wherein IP and OP almost give rise to similar lifetimes, wherein neither environmental factors nor the creep damage dominate. And another type of variation wherein it is called E prime, where IP loading conditions give rise to shorter life compared to OP. And the creep damage occurs only at the high loading amplitudes. So this I just give some important results which we have obtained on austenitic stainless steel, base metal and weld joints, and ferritic 9 chrome varieties of steels. We have investigated 9 chrome on moly steel and reduced activation ferritic martensitic steel, which are respectively used or potential or which is 9 chrome moly steel is the material for the steam generator components of fast reactor, whereas there is another type of similar steel which I'll be coming a little while later. So in this, in austenitic, in both of these materials, we have carried out IP and OP-TMF tests, and the strain rates employed compared to the isothermal cycling, the strain rates that can be used under TMF is far lower, or about a couple of magnitude lower in the case of thermomechanical loading because of the requirement of temperature cycling, and also the minimization of the temperature gradients. These limits the maximum strain rate that can be employed. Because of a higher thermal conductivity, ferritic steels permitted little higher strain rates compared to austenitic stainless steels, whereas in case of austenitic SS, we were able to do strain at 10⁻⁵, but ferritic steel we could go a little higher, owing to the higher temperature, thermal conductivity. Tests were carried out using the temperature intervals from a minimum of 300 to a maximum of 700 degrees centigrade. And for comparison, isothermal tests were also performed at the maximum temperature of the TMF cycling, employing the same strain rate and mechanical strain amplitude. And in my presentation, I will be using the term IF cycling to denote the isothermal testing. So this isothermal testing, when I'm comparing, I would always compare with the respect to the maximum temperature of the TMF. So strain compensation was done using this procedure, wherein the free thermal expansion under zero load during the initial ramp from ambient temperature to Tmax was enabled, and thermal cycling was introduced between the minimum and maximum temperature, allowing for the free expansion and contraction of the specimen. So the strain recorded by the extensometer is the pure thermal strain, which was obtained as a function of temperature, and strain temperature relationship was established, and which was used to continuously calculate and control the thermal strain during the test. So this, from the total strain that is sensed by the extensometer, the thermal component was calculated, and it was the calculated thermal component was continuously subtracted, and the remaining part, that is the total minus thermal strain, that is the mechanical strain, that was continuously recorded and calculated and controlled on a real-time basis during the test. So compared to the isothermal kind of cycling, there is one can, here you can see additional degree of imbalance on the stress strain hysteresis loop compared to the situation under isothermal condition. Isothermal condition, the tensile and compressive part of the stress strain hysteresis loop would be symmetrical, but in the case of thermal TMF, there is an asymmetry in the tensile and compressive part because of the differing temperatures during the tensile tension and compression strain of the cycle. So during actually what happens during the high temperature part of the cycle, the material will be deformed by plasticity and the creep plasticity and creep, provided temperature, the maximum temperature is high enough. But these deformation are applied to material that is just undergone half cycle of cold working during the lower temperature deformation, which makes the material a little bit stronger in the tensile part compared to what happens in the isothermal cyclic loading. So also the flow response will be higher. Higher compared to the isothermal case, and similarly in the lower temperature part anyway, because that's the temperature is lower, it will make it stronger in the compressive part also. So both the compressive and tensile parts, the response stress will be seen to be higher compared to the isothermal equivalent test at the maximum temperature of cycling. This typical results from the IP and OP TMF are shown here, and we can see that from this table one can see the mean stress variation because of the temperature difference. Normally the out of phase TMF leads to a tensile mean stress, and as against the compressive mean stress observed at under the IP cycling. The compressive mean stress under IP cycling because since the compressive deformation is taking place at the lower temperature gives rise to higher stress compared to the lower stress that is happening at the maximum temperature, which is during the IP cycling. So this sets up a compressive tensile mean stress under OP because we have a cold lower temperature coinciding with peak tensile loading. So this OP gives rise to tensile mean stress, and IP gives rise to compressive mean stress. This has a bearing on the life variation as well. Whereas the life cyclic life versus temperature, maximum temperature, when we plot, we see that below a temperature of about 650 degrees centigrade, out of phase led to a lower cyclic life compared to in phase. Whereas with increase in temperature beyond 650 degrees centigrade, in phase TMF give rise to a lower life compared to OP. What is happening is, with an increase in the temperature, the creep deformation was found to be more pronounced, leading to a life reduction in comparison with the out of phase. Whereas when the temperature is lower, the mean stress, mean tensile mean stress, which is built up under OPTMF, that proved more damaging rather than the creep damage. And an important observation from the viewpoint of the design is that the TMF gave rise to a lower life compared to the isothermal cyclic loading. So this signifies that the traditional approach is not a conservative design approach for these materials, and this similar situation is the case for both the base metal as well as the weld joint. So across the temperature of 620 through to 873 K, this is 350 to 600 degrees centigrade, as a function of mechanical strain, the cyclic life variation is presented here. And as we can see, for both the base metal as well as the weld joint, the life under in-phase TMF is shown to be the lowest, and the isothermal cycling at the maximum temperature gave the values almost in between the values that were displayed by the IP and OP-TMF conditions. And the creep damage that is happening under in-phase cycling was reflected in the form of extensive grain boundary cracking induced by the creep damage. So mostly the OP cycling was, it resulted in a pure transgranular cracking without much of creep or damage. Whereas there is mixed mode largely dominated by the creep cavitation kind of damage under TMF, I mean IP in phase TMF. This is being seen. We have investigated 316LN with various nitrogen contents also in order to establish the optimal nitrogen content for the best performance under TMF and creep fatigue interaction, etc. So similar is the situation across all the nitrogen contents. Here one can see the extensive grain boundary damage in case of IP cycling compared to mostly kind of largely mixed mode dominated by transgranular cracking in the case of isothermal and also in the case of out of phase TMF. So important thing is, even though the average temperature is much lower in the case of TMF, the creep damage occurs significant creep damage accumulation occurs. What could be one reason for this is that could be that in isothermal case, the kind of damage that is happening in the maximum tensile part, some of which gets reversed during the compressive part of the cycling. But in the case of TMF, for example, in the IP-TMF, the maximum tensile stress happens along with in coincident with the maximum temperature. Maximum temperature and peak tensile strength coincides. But as the temperature, as the strain comes from peak tension towards compressive, the temperature continuously goes down. So this prevents the reversal of the damage during the ramp down or the tensile to compressive ramp of the material. So this sets up a higher net tensile net damage in the case of TMF that has some role to play in the higher creep damage that is setting up, that is seen in the case of TMF, specifically IP-TMF, in comparison with the isothermal cyclic loading. So this is the typical dislocation structures that were observed under different testing conditions. This shows we have carried out at various temperature ranges. This first big figure gives an isothermal test at 550 degrees centigrade, typical dislocation arrangements that was seen. This planar slip bands, it was mostly typically seen, planar slip bands were seen. And as temperature was increasing, it was the dislocation structure changed to a wall-like or cell-like type of arrangement with an increase in the temperature. What normally these steels are very much prone for the current dynamic strain aging in the temperature range of about dynamic strain aging effects peaks almost in 550 to 600 degrees centigrade. So this is reflected generally in the form of planar, widely spread planar slip band in this alloy. But as temperature is increased, the tendency for cellular, dislocation structure happens, cross-slip happens, and this leads to cellular formation of dislocation cells, which is seen at high temperature, higher temperature TMF, and also under IP-TMF cycling. So, and a few tests in order to examine the influence of environment. Few tests were also carried out in vacuum. So this is a kind of setup that was employed for vacuum testing, and it was a few tests were carried out at a strain amplitude of 0.6%. As we can see here, this tests. This red solid line shows the in-phase cycling in air, and we can see from this, what we can say is the reduced environmental influence is much reduced under IP-TMF as against or in comparison with the OP-TMF. This suggests that the creep domination in IP tests, in IP test, because the life difference is not much in air compared to what is happening in the vacuum situation. But because the IP is largely governed by the creep deformation, so which is in vacuum, there is not much of a difference compared to air, as against the case with the OP TMF, wherein large difference is seen. And fractography also here also we saw extensive signature of creep damage, which manifested in the form of mixed mode fracture under 400 to 650 IP TMF. Coming to the steam generator material, the ferritic martensitic steel, this 9 chrome 1 moly, 0.2 vanadium, and a little bit of 0.1 niobium steel. This due to higher thermal conductivity and lower thermal expansion, this is the material normally preferred for the steam generator components of the FBR. In this material, it gains strength from mainly through three important factors. One is the large martensitic structure, and another is from the finely dispersed, distributed carbide particles, and another is the high dislocation density that is characteristic of these materials. Now, when it's exposed to high temperature, all these factors change. The large precipitates have a tendency to grow, and this leads to restructuring of the martensitic laths. The lath structure undergoes change. It becomes it gets structured into kind of a cellular structure, and the breakdown of the laths, and this implies, or this leads to a reduction in the strength, and the dislocation density also continuously comes down. And these factors, all these factors lead to a reduction in the strength of the material. And this was investigated under isothermal and in-phase and out-of-phase cycling at different strain amplitudes. In this case, as against the life variation observed in austenitic stainless steel, where we have seen IP cycling giving rise to a lower life. In this case, the situation was slightly different. You can see that out of phase cycling led to a lower lifetime compared to in phase. Again, across all the temperatures investigated. So this is a typical substructure. As I said in the earlier slide, the martensitic large structure in the untested condition can be seen, whereas it gets restructured, gets changed, and subcell substructure formation happens under IP cycling, and coarsening of the laths, etc. happens, and the precipitation, enhanced precipitation is also observed. These are probably the prior martensite laths can be seen here, which is replaced with a lot of precipitation that is happening inside. And another material was also investigated. It is referred to as lower or reduced activation ferritic martensitic steel. It is a slight modification of the 9 chrome 1 moly type of steel, where molybdenum is replaced with tungsten, and niobium is replaced with tantalum, because this is a fusion material, structural material for fusion reactor application for the test blanket module and the first one, plasma facing component of the fusion plant. As we know, the elements such as molybdenum, niobium, etc., give rise to a very long-lived isotope that makes the structural materials very highly radioactive during the operation. So hence, in order to reduce the long-lived isotope formation, it is normally recommended to replace this molybdenum niobium with low activation elements. So normal general this alloying elements are tungsten, vanadium, and tantalum. The molybdenum and niobium are replaced with this. And here also in this material, also we have done systematic investigations on the isothermal and thermomechanical fatigue. We can see, as you can see, the out of phase TMF leading to lower life compared to both in phase and isothermal loading, where you can see accelerated softening that is happening in OP TMF in comparison with both the IP case as well as the isothermal cyclic loading. So this is related to, as I will be coming to it a little later. This is also actually related to the oxidation associated damage, which will be seen in the next few slides. And another, there is also another factor which is leading to lower cyclic life under OP in the form of extensive cracking that is noticed under OPTMF in comparison with IP. In the case of IP loading, the cracks were lesser in number, and also the tips were relatively blunt compared to the IP. I mean, compared to the out of phase cycling. So here the tips, there were more density of the surface cracks, and the cracks were found to be, the tips were found to be much sharper compared to the case with the IP loading. Because maximum temperature and tensile loading, combination of this blunts the crack little more degree compared to what happens in the case of OPTMF, where the peak tensile loads occur with the lower temperature part of the cycle. Typically, what is happening is in the case of IPTMF, here the maximum tensile stress happening at the maximum temperature. Here, the oxide forms at the peak, oxide forming at the peak tensile load at the maximum temperature. When you reverse the strain, the oxide layer gets sparred off. In comparison, as against the cracking of the oxide layer that is taking place in the case of out-of-phase cyclic loading, where maximum temperature at the peak compressive strain, the oxide formed at the peak temperature at the maximum compressive strain, which on subjecting to tensile strain during the changeover from the compressive strain to the tensile part, the oxide formed gets cracked widely. So this gives rise to something like, in OPTMF, you can see a lot of damage associated with oxide cracking, as against the situations in isothermal and IPTMF case. Substantial cracking of this oxide layer coupled with the significant internal cracking, internal oxidation is seen in the case of OPTMF. So this coupled with the occurrence of the mean tensile stress, because tensile stress is much higher in OP compared to IP. You can see here in this the figure, tensile stress much higher compared to the other two cyclic loading. So a combination of the oxidation induced damage and the higher tensile stress gave rise to a lower cyclic life in the case of OPTMF in these material. It was the case both with the 9 chrome 1 moly steel as well as the reduced activation ferritic martensitic steel. So yeah. There's another important factor, important result I would like to show is the occurrence of serrations in this loop. That is all in the OPTMF, the dynamic strain. This alloy is prone to the occurrence of dynamic strain aging. In the temperature range of about 400 to 500 degrees centigrade. So in OPTMF, this happens in the peak, tensile side, where tensile direction is colder. In the case of OP, so the serrations were seen in the tensile, largely in the tensile part under OPTMF, and depending on the temperature traversed during the testing, the nature of the serrations also change. In fact, lower temperature serrations generally are of A type, and with the intermediate temperatures, they convert into B, and then higher temperature regime, we normally see the C type of serrations that are occurring. So all this is happening during the cyclic loading. Depending on the temperature traversed, the type of serrations also keep changing from A to B to C. And similarly, in the compressive parts of the stress strain loop, under IPTMF, the serrations, similar kind of serrations were seen. So occurrence of all these three mechanisms contribute to reduced cyclic life under OPTMF case. So some tests were done in a vacuum as well, And as you can see, the continuous softening that is happening in the air is not there when tests are conducted in vacuum. So this precisely identifies the damage due to the oxidation that is happening. And then lower life under OP DMF, which is seen in air, it is not there in the vacuum tests. Vacuum, you can we saw that the OP DMF has little higher cyclic life compared to the IP case. And this is a corollary can be drawn from our earlier tests which were conducted in the liquid sodium environment, wherein in air environment we have seen that this is isothermal creep fatigue interaction tests which were carried out earlier. This is not related to TMF, but since it has connection with the present results I've just shown, this in air, we see that compressive hold time gave rise to a lower cyclic life in air, whereas the compressive hold showed a higher life when tests were done in air. So the creep contribution could be clearly seen. It can be related to the creep damage purely, not related to any damage due to the oxide or environmental effects. In vacuum, the cyclic life was higher in tests were done in the compression hold. And coming to the creep fatigue interaction, we have done few tests on the traditional or conventional CFI, isothermal CFI comparison with the creep TMF loading, wherein we have incorporated the hold times at the peak temperatures and the cyclic life variation from the cyclic life variation or comparative variation between creep TMF and creep isothermal creep fatigue interaction. We have seen that the creep DMF shows a lower cyclic life compared to creep IF or creep fatigue, isothermal creep fatigue. You can see for all the temperature ranges investigated, the creep TMF led to a consistently lower lifetimes compared to the mag or the peak constant temperature creep fatigue. This this is similar to the earlier results. The creep IF or creep normal isothermal creep fatigue. This gives the difference in the fracture morphology between these creep isothermal and the in-phase. In-phase creep IPTMF. Similar to what is happening, what was noticed in the continuous cyclic tests, creep IP TMF gave rise to substantially more or significantly more creep damage that reflected in the form of the creep cavitation on the triple point cracking on the fracture surface. And we have examined the fraction of intergranularity, which was seen to be consistently higher in the case of creep TMF compared to creep IF cycling. This has similar exercises been done, though I have not shown, in the case of continuous cycling also, wherein we have observed, similar observations have been there. And I will just give a brief outline of the modeling of the hysteresis loops which we have attempted. we try to predict the hysteresis loops under thermomechanical fatigue using the isothermal database, for which a simple model by Skelton Webster, proposed by Skelton Webster, was employed. This we've carried out a test set, isothermal test at various temperatures at the steps of 50 degree, from 400 to 650 degree. The mechanical strain versus temperature waveform was plotted for the desired TMF loading and stresses corresponding to different strain values at the different temperatures of isothermal testing were obtained, and this gives rise to only a few points. But for the intermediate strain levels, we have plotted the stress temperature variation for different strain values in the temperature range using the LCF or isothermal LCF hysteresis loop data, and stresses for any desired combination of temperature and the strain were obtained using the plots, stress versus temperature plots obtained in the previous step. And this stress versus temperature was plotted for different strain values along both the ascending part and descending part of the hysteresis loop. And we have got somewhat satisfactory prediction of the hysteresis loops under thermomechanical fatigue based on the data obtained from the series of isothermal tests from the 402 carried out at different temperatures in the range of 400 to 650. And we have also tried to employ a couple of models for prediction of cyclic life under TMF. And one of them is the frequency modified damage function approach, which is proposed by Ostergren. This is a slight modification of the Coffin-Manson relationship, where the fatigue life is represented as a function of the maximum stress and plastic strain and the frequency of cycling. So predicted life is represented by this equation, whereas the frequency is the 1 by t plus delta tau, t tau plus delta tau, whereas the delta tau is the time per cycle during which the creep occurs. So in phase we have taken the time which it takes to go from the creep dominant temperature. Say in the case of this 3160 LN, it's almost like 550 to 650. What is the time taken for traversing this temperature? That has been taken to arrive at the effective frequency, which is the new term here. And these other are constants. And another approach was also used, which was proposed by it's a crack growth model proposed by Tomkin, where the crack growth rate is represented as this B into A, where the B is given by this expression as a function of the stress and the plastic strain. So sigma is the maximum response stress, and this Rm is the UTS at the temperature where the peak tensile strain occurs. So for this case, for this calculation, we have assumed initial crack length of the grain size. This was these approaches were used for 316 LN stainless steel. So this which had a grain size of 75 microns. So this was assumed for the initial crack length, and the final crack length was taken as 1.2 mm. So which was found from the from the tested samples, where we have seen that when the crack length reaches 1.2 mm, the fracture of the sample happens. So that was taken as the final crack length, and we can see that both these technique gave rise to prediction of cyclic life within largely within a factor of 2, both these on 3 months for 3 months is LNSS. And now just coming to the just to conclude my lecture. Isothermal LCF at maximum temperature led to lower cyclic life compared to TMF that led. It is actually TMF led to lower cyclic life comparison with isothermal. And with increasing temperature, in fact, the life the difference was narrowed down. And IPTMF proved more damaging in lower temperature regimes for 3 months. LN stainless steel, while more damaging in the okay. There is some small this one here, some small problems in this. Actually, isothermal TMF, isothermal LCF proved less damaging compared to OP cycling, compared to TMF cycling, whereas in the case of 3 months LN, IPTMF resulted in lower cyclic life. And higher tensile, higher stress response was seen in the case of TMF compared to isothermal cycling, and a satisfactory prediction of TMF life could be obtained using the isothermal database. Also, the loop also could be predicted based on this. And importantly, the study brought out the importance of the TMF database from the viewpoints of structural integrity and to establish, to achieve adequate design conservatism in the materials of which was applicable to both the austenitic as well as ferritic steels, including the austenitic SS weld joints as well. So I would, to end, I would just like to record my thanks to my colleagues, Mr. Kannan, Suresh Kumar, Prasad Reddy, Vani, Shankar, Mariyappan, and Mr. Srinivas Rao. So thank you very much for your patient hearing. Thank you. Thank you. Any questions? I would be happy to address.
Yeah. Thank you very much, Dr. Nagesha, for an interesting lecture which covered several aspects of the thermomechanical fatigue, and also talked about the what is called the significant points where it is important to take into design consideration the the thermomechanical fatigue, and between the in phase and out of phase, which is likely to be more damaging. Apart from that, you also covered something on the creep and fatigue interactions, and you talked about the modeling of this from the viewpoint of even considering it as a crack and then the growth of it. So it's very interesting. So let's kind of thank the speaker and first, and then let's move on into the questions which have been raised by the audience. So can I go through that?
Yeah.
Okay. So there is one question from Atib Ahmed Khan, who says that how have you measured thermal strain in the case of a thermomechanical loading?
Yeah. Thermal strain is actually what we do is initially we cycle in load control, keeping the load 0. So the thermal and cycle it from the minimum to maximum temperature, and the strain that is recorded by the extensometer during this thermal zero stress thermal cycling is the pure thermal strain. So this component, then the thermal strain is plotted as a function of temperature. So at every temperature we have the record of the thermal strain. So from the relationship, the thermal strain is calculated and controlled. In fact, it is subtracted from dynamically from the total strain which is recorded by the extensometer during the actual test. So the difference between the total and the thermal strain is the mechanical strain which is controlled during the test progression.
Okay. So there is the next question from Vinay Kumar Yadav. He is from IIT Roorkee. What are the internal constraints that causes thermal stress fatigue? As under LCF test, the loading frequency is quite low.
Yeah. What are the internal
constraints?
Internal constraints, internal constraint is by the bulk of the material. If you have a thick section, you have more internal constraints because you have a cooler interior, which is which restricts the sample, the material from expanding and contracting freely. So this gives rise to the stress. Maybe in some other, composites, etc., there will be second phase materials and other things will be also there. That will also add to the thermal stresses. That will also, influence the thermal stress occurring or building up in the material.
Okay, this is not the question from the audience, but from my side. If supposing thickness is one of the, the considerations for this constraint, would there be a chance that there will be a crack initiation from the inside of the material compared to the outside?
Yes. Crack initiation can happen in the inside material, definitely, because the stress will be higher. In the thermal stress would be higher in the with the specimen sample bulk. So internal crack initiation can happen. And when you're talking about high temperature cycling and considering the lower, very much lower cyclic frequency associated with this, there would be another factor. There quite a lot of contribution from the creep damage also, which also would give rise to cracking happening from the inner inside surface. So internal cracking very much
Okay.
possibility. Yeah.
So are there any telltale evidences to identify from any failures, whether it has cracked from the outside or from the inside?
In fact, the fractography itself can give, can show it up.
Okay.
Though in our case we have not seen, but the fractographic evidence can prove to be conclusive evidence can come for the internal crack initiation. Yeah.
I assume in your case, maybe because you are using mostly a tubular sample, right?
Yeah.
So where the wall thickness is less, so
Yeah.
your gradient in temperature between the outside and
Yeah,
inside is
purposefully,
not
purposefully we have used the thin, thin, so that
right.
to minimize the radial temperature gradients. Yes. Yeah.
Good. So there is a question from Dr. Sundar. Have studies been conducted on TMF with fold time at maximum strain or minimum strain?
See, hold times were in the maximum. We have conducted in under IP TMF. So where the hold times were imposed at the maximum temperature at the peak tensile strains. Yeah.
So if you do the fold time at peak strain, then
if we do at the compressive peak strain, that would be like creep, hold time imposed at the lower temperature part of the cycle. That may not have much, that may not cause much degradation in the cyclic life. Though of course we have not seen that. We have carried out OPTMF at the compressive, but IPTMF at the peak tensile, because we wanted to have the hold imposed at the maximum temperature of the cycle only. Yeah.
So that results in stress relaxation, right?
Yeah, correct.
Okay. So then there's one more question from Mustafa Kazim. He's from IIT Kanpur. Can you please comment on the effect of DSA on the cyclic mean stress in IP and OP?
Cyclic mean stress. I have not. We have not correlated with the mean stress and DSA. Of course, when DSA occurs, the DSA also will give rise to the stress. Shifting the. It will increase the stress in generally. The occurrence of DSA itself will increase the stress. So in the case of OPTMF, as we have seen, ferritic steels, OPTMF, the dynamic staging happens in the tensile part, because the lower temperature occurs in the tensile, and the ferritic steels lead to DSA in the lower temperature side of this cycle. So as such, we have the OPTMF giving rise to mean tensile stress, but the occurrence of dynamic staging might be responsible for still an increase of the mean tensile stress to even more tensile. It could be. Yeah.
So you're saying that the tensile stress causes
tensile mean stress may have the strong function of the occurrence of DSA also, though this is perhaps one can investigate by carrying out at different strain rates and seeing. So that possibility is that we can do at slightly different strain rates to avoid the occurrence of DSA, and see whether it has any influence of the variation of the tensile, mean stress. So at this point, I cannot really give more complete answer on this question. Yeah.
Okay, I have my curious question. See, normally in these studies, you will find that your heating rate is kind of probably much faster than the cooling rate.
Yeah.
So does it have an effect? Because eventually your thermal strain rate is different for heating part versus the cooling part.
Yeah.
So has there been any evidence that it comes in the picture when you understand the mechanics of the damage in the TMF regime?
No, it will have. But in our case, what we have done is we have the cooling. Cooling is always a problem. Actually, heating is relatively easier and simpler, but cooling is a problem. And but in our case, we have a water cooled grips, which aid in the fast cooling of the sample. And apart from this, we also use some air jet on the sample to enable fast enough cooling. So the heating and cooling rates were both constant throughout the cycling. So yeah.
Because many labs where I know they have this purely the air cooling system, the heating rates are different from or are typically twice the the cooling rates.
Yeah. I see what your point is much would be very important if you have much faster heating and cooling rates. In our case, the thermal cycling rate was about 2 to 3 degree per second. So if we go for 5 to 10 degree, etc., then there will be problem. Yes.
So yeah, there I think again the associated oxidation and other things will also pick up over there, right?
Yeah.
So what is the maximum temperature to which you had tested this thermal
See,
size? Like
in for 316Ln, we have gone up to 700 degrees, sir. But
Kelvin, or
yeah,
is it Kelvin or centigrade?
700 degrees centigrade.
Centigrade. Okay,
Yeah,
973 Kelvin. Okay.
yeah, 973.
Okay, good. I think, are there any more questions from the audience? If there's anything, can you just type it in the chat box? Or if somebody wants to speak up, he can also do that.
Yeah, Mr. Raghu, so
Yeah.
my question is not going into chat box, so let me ask it. Normally we plot the stress versus number of cycles curves in fatigue studies using the amplitude stress, whereas you have used the peak stress. So is there any specific reason that you use peak stress to study the stress versus number of cycles behavior? Secondly, in the linear elastic fracture mechanics, we typically consider an initial prior introduced crack length because we need it by the entire theorization. You used 1 grain size as initial crack length. This is a standard method wherever we have not introduced any prior crack, or we want to study where we are looking at the possibility of the crack initiation due to the mechanical loading or mechanical thermal loading at the weakest point. To use the LEFM, we can consider 1 grain size as the initial crack length and go forward applying the model. Thank you.
Is that Professor Ragela from
Yeah.
BITS Hyderabad?
Yeah, good evening.
Yeah, good evening. Yeah, okay.
Sir, yeah. Coming to your first question, in generally in isothermal fatigue, even if you use the stress amplitude or the maximum stress, it will be same. Generally, the tensile stress at peak tensile and peak compressive, in general, there will be identical. So it will be same. If you use a peak tensile stress or the stress range, you will get the similar kind of behavior in the case of isothermal cyclic loading test. But coming to TMF, since the temperatures are different, temperature corresponding to the compressive and tensile parts are different, the stress values, peak stress values will also be significantly different. So in this case, we normally plot both the tensile as well as compressive stress response to make it to give a more complete picture of the variation of the CSR during the test. So I think, is this clear, sir?
Well, Professor Ragela?
Yeah.
Okay. So,
okay, the second part of his question was related to the initial crack size of 1 grain that I have taken. I have just taken it because it's normal practice to take the initial crack size as 1 grain diameter size. If you don't detect any presence of any crack, so it is normal practice to assume it to be a grain, the size of the grain. So because grain itself is a kind of a defect, so it is taken as the initial grain size. Initial the crack length is taken as that of the equal to the grain size. So that is the only that is the reason why we have taken it, assumed it to be the grain size.
yeah, I mean, but this is something, a lot of interest, and then also there could be a debate.
Yeah.
Supposing we take the initial crack size as that of a grain, then do you get to see any kind of short crack or a small crack effect in TMF experiments? Because normally, a lot of things have been spoken about the small crack size and then how they
Yeah.
behave when it comes to crack growth and things like that. So, is there any take from your side?
At this point, I cannot really comment on that short crack behavior. So
Okay.
I will look into that too.
I mean, I don't know if anybody else in this audience is able to comment on that. Is there anybody who really worries about small crack size and then the TMF? Laksundar?
Well, it's a question of being able to study it. So I would imagine that our challenge is more in designing experiments where you can actually track the effect of crack size. Perhaps one way to proceed in the future. My single track mind tells me that if we employ program loading, we can mark the fracture surface and get to study this behavior much better.
Yeah.
Oh, you mean like program the waveform for TMF and then study it?
Not the waveform. For example, on the equipment, you have a couple of cycles with TMF and then a couple of cycles at lower temperature just to mark the crack, without affecting the damage process, and then get back to thermal cycling and then look at the result over there on the fracture surface.
Oh, okay. That sounds interesting. Yeah.
We have done that, Raghu, if you remember, at room temperature under the Falstaff spectrum. You
Yeah,
have
room
yourself
temperature,
studied
yes. No, room
20
temperature.
microns up,
Yeah, right. But
part
I
through
was just
cracks,
looking
so it's
more at
practical.
yeah, I was just looking at whether it has been extended for the the high temperature TMF conditions.
Mm-hmm.
Yeah, right.
I had
Okay,
a
good.
question, if I could butt in, if you'd
Sure,
let me, for Dr. Nagesha. And that is, TMF testing is very expensive because of the thermal strain aspect. So now, if I were to use uh, a thick specimen, go the opposite way. Instead of a tubular specimen, go for a 10 mm dia or 20 mm dia with a very small hole to cool it from inside. And then just do TMF under stress control without bothering about the strain, the thermal expansion. Because as you mentioned in your introduction, the reason why we study TMF is because of the gradients in temperature in components. So I can now work with say a 20 mm thick specimen and cool it from inside and then cycle it just by induction heating.
Actually, I think this kind of tests are also being done. In fact, what you are probably referring to is thermal gradient stress fatigue or thermal gradient
That's right.
mechanical fatigue. I think that's some.
Absolutely.
Yeah, there are in the recent past there are some studies related to this. So in fact, I was also planning to undertake some studies on in this area also, where we'll use a thicker wall, higher wall thickness and impose the loading through under stress control. So this is there are some reports on some superalloys which I was going through, where they've seen under identical conditions they have compared kind of both TMF and this thermal gradient stress fatigue and comparison with the isothermal. And substantial life reduction compared to the classical TMF has been reported under gradient fatigue. And this we also, in fact, so thinking of carrying out some studies in this direction as well. And there is also thermal, stress thermal ratcheting kind of things also in combination with the stress controlled TMF. So that also we have initiated a few activities recently.
I would imagine that if you had a very thin, a very small dia hole in the specimen, you could pass, for example, liquid nitrogen or something and keep it at real low temperatures.
Correct,
then
correct, correct, correct.
use applied mechanics computations,
yes.
which are very
Yeah,
reliable
yes,
to compute
yes,
the temperature
yes,
gradient and therefore
yes,
translate it to thermal strain.
yes, yes,
And you wouldn't be restricted in your rate. You can go to,
yes.
instead of one cycle every 100 seconds, you can go to even, maybe 20, 30 seconds.
Yeah, yeah, yeah. Thank you. Well, I'll come back to you on this some point.
Oh, maybe we could do some work together.
Sure. Yeah. Sure, sir. Sure.
So there
Thank
is
you.
a comment from
Thank you.
Mustafa Kazim from IIT Kanpur. He says that they are doing some analysis for TMF of micro crack from one grain to a long crack, and they are in the process of post-processing the results.
Yeah.
Okay, so anyway, if there are no more
Thank you.
questions, I think we will kind of thank Dr. Nagesha for this wonderful lecture, and let's kind of give a round of applause through the online mode. And of course, some of you were not able to see him on the camera because of some technical glitch that he has had. But nevertheless, I'm sure that the topic and the lecture was quite illustrating and gave a lot of insight. So I will once again thank on behalf of the Indian Structural Integrity Society and then the Center for Safety Critical Systems of IIT Madras. Big thanks to Dr. Nagesha for this lecture. So for the purpose of the information, the next webinar will be on March 11th, which will be delivered by Professor Praveen Kumar from Department of Materials Engineering, Indian Institute of Science. He will talk on the effect of electric current on pre-cracked thin metallic sheets from crack healing to their propagation. So this is the title. So I request you to join. You will get all the meeting links and other details shortly from our office. Thank you very much. With this, I kind of conclude today's webinar.
Thank you. Thank you, Professor Raghu Prakash. And thanks to InSIS again for giving me an opportunity. Thank you very much.
Good. Welcome.
Yeah. So I will exit.
Yeah. So, Bharti, can you just stop the recording and close the session?